So here we are in section 3.2, and we're going to talk about the fundamental theorem of calculus. Now, how do you know anything in math is important? Well, they call it fundamental. That's a big tip-off. This is kind of important. This is kind of a big deal. So make sure you get this section. It's not hard. It's just important. Okay, so here we go. Um, we're going to figure out what the fundamental theorem of calculus is saying through a little bit of experimentation. So letting m of t equal 65t plus 15, where m is measured in miles traveled on a trip and t is measured in hours since you started driving. Okay, so we plug in the t, we get out a m. So for example, if I substituted in, I don't know, 1, what would that mean? Well, that would mean it would be 65 plus 15, so that'd be what, 75, 80. So this would mean after traveling for 1 hour, we have gone 80 miles. All right, so now, can you pause the video and answer this question? Say, how far did you travel between hours 3 and 5? Okay, so go ahead and see if you can figure out how to answer that question, and then unpause the video and see if you do it the same way that I did it. Okay, so here we go. What I'm going to say is to figure out how far I traveled between these hours, if m tells me my total distance traveled, well, I got to see how far did I go at 5 hours, how far had I gone at 3 hours. So when I substitute in 5, let's see, 65, we'll use the handy dandy calculator, it helps out a little bit. Do 65 times 5 plus 15, that's going to result in 340. Okay, so after 5 hours, I had traveled 340 miles. Similarly, we're going to do the same math, but now do it for only 3. So then after 3 hours, I had only gone 210 miles. So how far did I travel between the hours of 3 and 5? Well, that would be the difference, right? That would mean, okay, it would be the distance I traveled at 5 hours minus this distance I had traveled at 3 hours, and then that would tell me how far I went between them. So let's go ahead and say this would be 340 minus 210. So therefore, this would result in what? 130 miles. So between the hours of 3 and 5, I had traveled 130 miles. Okay, now let's calculate the integral from 3 to 5 of m prime of t. All right, now, so remember from section 3.1 what this notation is saying to you? This is area under the curve, right? Okay, so the first thing we're going to need to do is, and if you want to pause the video and try this, you have all the skills you need, so you can try this. But what I'm saying is we're going to do it geometrically. We're going to do it by finding area under the curve. So see if you can do that. Okay, so here's what we're going to do. First thing I need to do is say, what is the derivative of m prime? Well, all right, what is the derivative of m? What is m prime? So that would be what? 65. So what this is saying to me is I want to do the integration. I want to find the area under the curve of this function of 65 dt. Well, so if we draw the graph of that, we'd say, all right, well, how do you graph the function of y equals 65? Well, that means at 65. Here, I'm going to make a little bit of space for myself and say what the units here on this axis was. The derivative would be miles per hour, and then our t-axis would just be measured in hours. Okay, so a horizontal line of y equals 65, m prime equals 65. How do I graph that? A horizontal line. Zoop. All right, and I don't want all the area under the curve. I only want to measure from hours 3 to hours 5. So how do I find the area under the curve here? Well, hopefully you're saying, hey, that's just a rectangle with a width of, let's see, the width would be 2, and the height would be width of 2 and the height of 65. So therefore, this thing is equal to, I would calculate this by just doing 2 times 65, and that would make 130. Whoa, look at that, 130 miles. Okay, I'm pretending a little bit. I knew that was the answer. Does it make sense? Think about what we learned in the last section. When we find the area under the curve, it's the units of this axis times this axis. So therefore, it's miles per hour times hours, which leaves us with miles. So for part C, what are we going to say? Super interesting. The integration when we're dealing with something like this, the integration for a definite integral where we have endpoints is describing the change. How much did you change from 3 to 5? What was our change in distance? What was our area under the curve? Well, it could also be found by saying just take your distance in 5 hours, take your distance in 3 hours, and subtract it. Holy cow. That is the fundamental theorem of calculus. That's what this is saying, is we now have we have a new way of doing this. You can either do it the way you already know. You can find the area under the curve, or there's a big or in between. It's you find the area under the curve, or what we can say is find the end value and subtract it from the start value. Now notice, what are they substituting it into? They've got a little bit of funky notation going on here. Notice in here we have a lowercase f, and outside we have an uppercase f. So what they're doing is, what they're showing you here is lowercase f of x is the same thing as the derivative of the uppercase function. Okay, so notice that's what I have going on, right, what I've noted for you guys in your notes right here. So what they're saying is, if you had an original function, the derivative of it is lowercase f. So as long as you're clear on this notation, what they're saying here, and we'll do a couple practices of this to really help you see what's going on here. But the big idea is we now have two methods for doing these problems. You can either find the area under the curve by drawing millions and millions and millions of little rectangles and adding them all up, or you can say, I need my capital F. This is the lowercase f. We already did the derivative. I need to undo the derivative to get my capital F, and then just plug in my end value, substitute in my end, substitute in my start, subtract the two, and presto changeo, we've got our area under the curve. We have our integration. So here we go. Now, we don't know any antiderivative rules yet, but you can most likely figure out a few of them just by being observant. So let's calculate this problem here. Let's calculate the area under the curve of this curve. This is a quadratic going from 3 to 7. Okay, and then, but let's do it using the fundamental theorem of calculus. So, and notice what they've given you here. What they said in this section, we're always going to give it to you. They're going to say, we know capital F of x is x cubed divided by 3 plus 3x squared divided by 2 minus x. So now, if you think about it, what would f prime of x be? What would we don't normally do this, but just to kind of show you, what would the derivative of this be? Well, we'd bring the 3 out to the front, so that'd be 3x squared divided by 3. Plus, now here you bring the 2 out to the front, so this would be 2 times 3x divided by 2, and then that would be minus 1. Now, after a little bit of simplification, you'll see that 3 and that 3 divide, that 2 and that 2 divide. Holy cow, look at that! That's our lowercase f. So what they've done for you is they've given you everything you need, and you can verify very quickly that these capital F's, if you do the derivative of these, the derivative of this will lead you to what you have in there. So therefore, we know this is going to apply to the fundamental theorem of calculus, which again says the integral from a to b of lowercase f of x dx is equal to the uppercase evaluated at your end, the uppercase evaluated at your end minus the uppercase evaluated at your start, or aka the antiderivative, the undo the derivative. If f has already had the derivative done, let's undo it. And that's what we're going to be doing going forward in the next section, is saying, starting with this, get me to here. So you can kind of play that game and see if you can think backwards on your derivative rules for now and see if you can figure out what the capital F would be. So nonetheless, let's do this problem. All right, so what this is saying is the integration of 3 to 7 of x squared plus 3x minus 1 dx. Well, the fundamental theorem of calculus says, take your function, take your capital F, and substitute in your values. Now, what I will show you is there's a fun little notation that we're going to use for this to show, okay, that to show that we haven't done our substitution yet. And what we do is you just put a little bar at the end. So you can see what we're saying here is I need to substitute in all of my values for my x's, where 7 is my end, and 3 is my start. Okay, so let's do that. Let's plug it in. So here we go. It's going to be 7 cubed over 3 plus 3 times 7 squared divided by 2 minus 7. Now note, this would be my f of b. I've substituted in my high amount. Now I need to subtract, and I need to subtract my low amount substituted in. So that'd be 3 to the third divided by 3 plus 3 times 3 squared divided by 2 minus 3. And then, so this would be my f of a. So I have my high substituted in my capital F minus my low, or my end minus my start. All right, and now comes just a tiny bit of calculator button pushing and getting a number. So I'm going to go ahead and pause the video while I do that. And what my calculator told me is that this comes out to 484 thirds. Okay, or as a decimal, that would be approximately 161.3 repeating. And so note, most of these problems are going to want it exact, so go ahead and do it, get exact using the math frac in your calculator. Okay, so that's how you do this. We just found the area under the curve without ever doing area. How awesome! We use the antiderivative, we use the capital F, and we just substitute in our end, substitute in our start, subtract the 2, and there you go. All right, so now pause the video, you try this one, and also see if you can see what is the antiderivative of this. What would it be? This is the answer to the derivative. We've already done it. What would it be when we started? All right, pause the video, give it a shot. Okay, so now you can see, hopefully you saw, all right, if you're just thinking with your derivative rules backwards, 1 over x is the answer, which means the question was natural log. So therefore, to do this problem, it's all we're going to simply do is say, all right, I need to take my capital function, my capital F of x function, and substitute in my high amount minus my low amount and get an answer. Now, if we wanted an exact answer like in Math AS, this would literally be your answer. Well, actually, you could actually simplify a little bit, couldn't you? Using log rules, we could say this is 17 divided by 1.5. So therefore, what would that be? I don't know how much that's going to clean up. That would be the natural log of, yeah, it's not going to clean up at all. We just have to multiply by 2 because nothing goes into those. Yeah, so that would be 34 thirds. So either versions of these would be your exact answer, or your decimal approximation, which is going to type in the calculator. So it'd just be the natural log of 17 minus the natural log of 1.5, and that would give us 2.4277-ish. All right, so fundamental theorem of calculus, like I said, not hard, just really, really important. Okay, and so now let's do another one here. In this problem, we're going to first calculate the integral of this using the fundamental theorem of calculus. And notice we've already given you that capital F. And then what I want to do is I want to do it once in the calculator. Let's just verify our answer by using the calculator to show the area under the curve. Okay, so here we go. The antiderivative of this, and if you want to do this, go ahead and pause it on your own. Hopefully you've gotten enough practice at this now that you're seeing it. Okay, so here we go. We're going to substitute in our high minus substitute in our low. All right, so let's see. 4 squared is 16. 16 divided by 2 is 8. 8 minus 4 is 4. This whole term is just going to become 0, so the answer is 4. Now, let's show that in the calculator. Now, there's a couple different ways to do it in the calculator, but I want to show you kind of graphically so you can visually see what's going on here. And what we're going to do is say, I want to know the area under the curve of this function. So what I'm going to do is literally just type in that function. Just type in x minus 1. Okay, so I'm going to just do a standard window. I'll do a zoom 6. Okay, zoom standard. All right, that kind of looks like what we would expect. So now for getting the area under the curve, going from 0 to 4, if you in your calculator, you'll notice in the top row, right above trace, there's a button that says calc. So what we're going to do is press second trace to bring up the calc. Now, you'll notice on line 7, that might look familiar. This is the first time you're seeing this. It's a new symbol, but you actually know what it means now. It means integrate. So what we're going to do is we're going to do option 7, and we're going to do our lower limit. Now notice it's saying, what is your lower limit? And the easiest way to do this, I think, is just literally type it in. I want to type in 0, so I just hit 0. Lower limit, x equals 0. Hit enter. Now, what's my upper limit? Well, that's 4. Upper limit, and there we go. And you can see it now shaded the area for us, and it's showing us dx, the integration of f of x dx is equal to 4. We get the same thing. And if we wanted to, we could say, all right, doing a negative 10 to 10, negative 10 to 10 doesn't really make a lot of sense because we're only going from 0 to 4. So what we could do is do our x values going from literally 0 to 4. And now when we do that same thing, you'll see that the window is a little bit better. We still could have played with our y values a little bit, but you can get the idea. We shaded under the curve, then we shaded over the curve to give us a total of 4. Okay, so I hope that helps. I hope you can see how to use the calculator to do this. I hope you get that big idea. So let's take a look at this next problem. Calculate this function using the fundamental theorem of calculus, if you know this, but make the assumption that negative areas can't exist. So when we look back at that calculator, you'll notice we had some area under the x-axis and some area over the x-axis. So this stuff on the left here was actually negative. So what do we need to do? How are we going to do this where if the person says, no, negative doesn't make sense. We're talking about total miles on the odometer. You can't do negative miles when you're driving. Even when you're in reverse, they still count as positive miles. So what are we going to do? Well, what we have to do is we say, all right, we've got something like this, and we've got some area here that's negative, some area here that's positive. We need to find out what this area is, and let's just pretend it was negative 2. Okay. What we need to say is we don't want it to be negative. We need to instead multiply that by a negative 1 to make it into a positive 2. All right, how can we do that? Well, what's the important things to know? To be able to split this area up into 2 different pieces, to be able to say where's the negative area and where's the positive area, we need to know where the x-intercept is. So what we can do is just take our function, say all right, our function here is y equals x minus 1, and we say I need to know where that x-intercept is. Well, what do we know about all x-intercepts? The y value is, that's right, 0. Yeah, I'm sure you said that. Okay, so therefore we know it occurs at x equaling 1. So what we're going to do now is do the exact same problem, but we're going to break it up into 2 integrations. We're going to first integrate from 0 up to 1. And if you stop and think about it, it's saying this area, if we were to do this, you can see it in the calculator very quickly. So when I integrate from 0 to 1, what you can see is we get an area of negative 0.5. So what I want to do though is instead of making it negative, I want to multiply it by a negative 1 to make it positive. So I'll just throw a negative on the outside of it. Multiply by negative 1. So take your answer, multiply by negative 1. Then I need to add that to the integration going from 1 to 4 of x minus 1 dx. So therefore, when I do that, that would be the positive area, right? That's above the curve, so they're above the x-axis. So therefore, just leave it alone, just add it. All right, so now doing this problem, again, we can do it by hand, saying, all right, I know what I've got going on here. I'm going to do, and I'll write it down below it. Let me just scoot this to the side. There we go. Oops, I lost my 0. Okay, so what I'm going to do is write it down below. So when I do this integration by hand, we're going to say I want my function that I'm substituting into, and I need to substitute in the high. So that's going to be 1 squared divided by 2 minus 1. That's the high. Minus the low, which would be substituting in 0. So it's 0 squared divided by 2 minus 0. And it's this whole answer multiplied by a negative 1. Plus, now we'll do the same thing again, but we're going to do it for the other integral. So you can see this yellow piece here makes this whole thing here. Okay, then this blue piece, what I'm going to do here in blue, this piece here is going to be this next part. So again, we're going to say, what's my function? It's x squared, so it's going to be 4 squared divided by 2 minus 4 minus, then I have to substitute in my low, which would be 1 squared divided by 2 minus 1. So now when we substitute all this into the calculator, the calculator did already show us, you see this is all the blue, the calculator did already show us, we know, hopefully, that this area should come out to be negative 0.5. This area here should come out to be negative 0.5. Let's verify that. So it's negative 1 squared is 1 divided by 2 is 1 half minus 1. So therefore, 1 half minus 1 is negative 0.5. Then we're going to multiply that by a negative 1 and make it into a positive 0.5. All right, so then over here we've got 4 squared is 16. 16 divided by 2 is 8. 8 minus 4, that's 4. Minus, let's see, 1 squared is 1. 1 half. 1 half minus 1 is a negative 1 half, or negative 0.5. So simplifying this a little bit, I have a negative 0.5 times a negative 1, which would make it into a positive 0.5, plus 4. Then here again I have another plus 0.5, so that's going to result in a total of 6. Alright, so hopefully that makes sense. Now let's verify that in the calculator very quickly. We knew that the negative part was 0.5, so now let's go ahead and calculate our integration for the second derivative, going from 1 to 4. And there we go, 4.5. So we got the same thing. We got from the blue side, from the right hand side. Whoops, I missed my highlighter. Come on. We got 4.5. And there we go. And from the other side, from the yellow side, we got a positive 0.5, which gave us a total of 6. Perfect. Okay, last little skill I want you to play with is just kind of thinking about a problem like number 6. Determine the approximate values for A that would result in a local maximum. Okay, so if we're trying to find a maximum when we're integrating from 0 to A, where would I be going up? Where would my integrals be increasing? Well, starting from 0, you can see these areas are getting more area, more area, more area, more area, more area. We're still shading above the curve. We're still shading above the curve, so above the x. So therefore, all these would be increasing my areas as I add up my little rectangles. And you can see they'd all be positive up until we reach about, I don't know, what do you think, 3.2? Okay. Then after that, our areas are below the x-axis, so therefore those would be negative. So therefore, I would have a local maximum in my area somewhere around 3.2. Are there any other values that might do that? Well, so, and if you kind of imagine what's going on with your area is, I'll do it kind of here in red. I would start off with area 0, then as I go, I'd be getting bigger and bigger and bigger and bigger, and then at 3, I would be kind of leveling off, or 3.2, I'd be leveling off. Then what would be happening? My areas now are negative. So my areas are going to be going down, 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 up until I reach about 6.3, right? So therefore, for this next section here, we're going to be going down, 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 until we reach somewhere in the ballpark of 6.3, and I don't know what the actual area, my total area would be doing, but I just know it's getting lower. And then the question is which one of these is bigger? And to me, it looks like the green is bigger. So maybe I would argue we're going to dip down into the negative areas, right? And somewhere in there. Then after that, what's going to happen to my areas? Well, we're back in the positives, and my areas are getting more area, more area, more area, up all the way until I reach about 9.4. Sure. So what's going to happen? We're going to start going up, 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 and we're getting really positive. This is way bigger than the other ones, so we're getting really positive area up until about 9.4. So it's just a guesstimate. We're not really caring about our actual numbers. My real question for you is just, you can see our areas are increasing up until about 3.2. We're decreasing because our areas are negative up until 6.3. Then we're increasing again up until about 9.4. So I would have local maxes at x equals 3.2 and x equals 9.4. So similarly, where would I have a local minimum? Well, and again, my local minimum would happen at that end of the green, if you haven't picked it up, somewhere around 6.2, 6.3, whatever we said that is. Okay, so play with that idea, see if that sticks with you. And best of luck in this section. After this, we're kind of done with the theory for a little bit, and we're going to go on to derivative, or antiderivative rules. So make sure you get the theory really strong because we're going to need it. Okay, best of luck.